Before we get going with today's new material, I just want to go over all of the p variables because we have p meaning a whole variety of things here. So first, we have p and p hat, and we've talked about these before. P is the population proportion. So that's the proportion for the whole group. Maybe it's something like I know that 52% of adults in the US voted for Prop A. Okay, so I'm saying something about the entire population. Now that's different from P hat. P hat is the sample proportion. So that might look like, in a sample of 100 adults, 57 said they'd vote for Prop A. And so to get the sample proportion, we would say p hat equals 57 over 100. So sometimes we use proportion and percentage interchangeably here, but the important piece is that the population proportion, p with no hat, is talking about everybody. And p hat, the sample proportion, is talking about the sample. It's talking about a smaller group. Now, we also have P sub zero. So P sub zero is the null hypothesis value. And this is on the side with P because these two are generally connected. So if my null hypothesis in this case might be something like P equals 0.52, my alternative hypothesis might be something like P is less than 0.52. And it's these numbers right here, the 0.52 on either side, that are the P0. So it has to do with their position in the null and alternative hypothesis. And the last P we have is the p-value that's the result of a hypothesis test. Okay, so this is the p-value that we get where we say, okay, is it small, in which case we reject our null hypothesis, or is it big, in which case we fail to reject our null hypothesis. And remember that this P is a probability. It's the probability that we see the data or the sample that we're getting if we assume that the null hypothesis is true. So it's a conditional probability. Now, let's just look at an example to sort of think about from a very high level what the p-value is telling us. So here we have two different students doing a coin flipping experiment. And in both cases, they have the same two-sided alternative hypothesis. I'm sorry, my pen is in the way. Let me move this over here. That was not a good spot. How about up here? That P is not equal to 0.5. Now, remember, we've talked about this in previous videos, but the null hypothesis P is not equal to 0.5 is the same thing as saying that the coin is not fair. Okay. So student one flips the coin 20 times. And if we count the number of heads, I've got 1, 2, 3, 4, 5 heads. So for this student, their sample proportion is 5 out of 20, which is 0.25. Now that's pretty far from a 50-50 split, right? That's pretty far from looking like a typical fair coin. For the second student, and I'll highlight this one in green, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 heads. So for the second student, p hat is 9 over 20, which is 0.45. Notice that's much closer to 50%. So the question we want to answer here is, without calculating the test statistic, without calculating the actual p-value, which one is going to get a smaller p-value and why? Okay, so if we have p hat equals 0.25, that's pretty far from 0.5. This is kind of unusual. And unusual tells me that the probability of getting 5 heads, if I assume that the coin is fair, is, I mean, it's not a big number, but it's smaller, right? This is going to be a smaller value. Whereas if my p hat equals 0.45, that's closer to 0.5. That's, more normal. Okay. And so in that case, the probability that I get 9 heads, if I have a fair coin, is going to be a bigger value. So in this case, student 1 is going to end up with the smaller p-value. Student 2 is going to end up with a bigger p-value. So that's just to give us a little intuition about how p-values work. Now, let's do a problem from beginning to end to sort of practice all of these ideas. So problem 3 right here. Health professionals are often concerned about our lifestyles and how they affect our well-being. A group of medical researchers knew from previous studies that in the past, about 39% of all men between the ages of 45 and 59 were regularly active. Because regular activity is good for our health, researchers were concerned that this percentage had declined over time, right? They're worried that people are becoming less active over time. So for this reason, they selected a random sample without replacement of 1,927 men in this age group, and they interviewed them. Out of the sample, 680 said they were regularly active. We want to perform a hypothesis test to determine whether the portion of regularly active men in this age group has declined. And we're going to use a significance level of 5%. So that's an alpha equals 0.05. Okay? So we need to start with our hypothesis. So remember, our null hypothesis H0 has to do with what we're assuming to be true. And so what we're assuming to be true is the information from those past studies, that 39% of all men between these ages are regularly active. So we're assuming that the proportion of men in this age group that's active is 39%. Okay. So our alternative hypothesis, I know right off the bat that I'm still going to be using p and I'm still going to be using 0.39 because those values don't change. My only choice is what symbol am I going to put in the middle here. And my options are a not equal to sign, a less than sign, or a greater than sign. Okay? And I have to decide that based on the language of the problem. Now, it's generally in the last sentence. So here I'm going to reread this last sentence right here. So perform a hypothesis test that will test whether the population of regularly active men in this age group has declined. So I'm only interested in if the number has gone down. If people are more active, I don't really care about that. I'm just interested in if the number has declined. So because of that, I'm interested in this proportion being less than 0.39. I'm interested in the number getting smaller. So that's my null and alternative hypothesis. Now, to prepare, I need my significance level, but I've already got that right here. I've got my significance level. And the other thing I need to do is check my conditions. So one of my conditions is that p times n is greater than or equal to 10. So let me grab my calculator real quick. So I need to do 0.39 times the total number of men in the study, which was 1927. And so 0.39 times 1927 is definitely bigger than 10. It's 751.53, which is definitely bigger than 10, right? I just need it to be bigger than 10. I need that these events aren't super rare. And then if I do 1 minus p times n, which is going to be 0.61 times 1927, I get 1175.47, which is also definitely bigger than 10. So the other things I need are that this is a random sample, and it is, right? We're told that we're selecting a random sample. The other thing that we need is a large population, right? You can't sample too many people out of the population. So here I have to ask myself, is 1927 bigger than 10% of all men? Even if we were just restricting ourselves to this age group, even if we were just restricting to the US, there are still more than 10,000 men in the country, right? Or 20,000 men in the country. So because of that, this, large population, we definitely have a large population of men. We don't need to worry about that in this case. Okay. So the next thing that we're going to do is use our calculator to find our p-value. Now I'm doing a one-prop z-test here. And so when I go into my calculator and go to the one-prop z-test menu, it asks for a couple of things. It asks for p sub 0. So remember that p sub 0 is the value coming from our null and alternative hypothesis. So in this case, that's 0.39, so 0.39. Then we need our x and our n. And so our n is our sample size. In this case, that's going to be 1927. And x is the number of people who said that they were regularly active out of this sample. So going back up, that's that 680 right here. Okay, so my x is 680. How many of these men said they were regularly active? The last thing I have to select is which symbol to use for my proportion test. And in this case, because my alternative hypothesis right here has a less than sign, I want to select the option with the less than sign. So that's going to be that it's less than p sub 0. And so after I put all of that in and I calculate, I get my printout, but the most important part is the p-value, of course. So my p-value is, it says 4.177 and then a bunch more numbers, e to the negative 4. So remember that e to the negative 4 is scientific notation. So I could rewrite this as p equals 4.177 times 10 to the negative 4th, which moves the decimal place 4 spots. So my p-value ends up being 0.0004177. That is a very small number. So when my p-value is very small, I reject my null hypothesis. So I'm going to come down here and I'm going to reject my null hypothesis. I can even, and I like this, I find it helpful, as soon as I write down reject the null hypothesis, I come back up to my null hypothesis and I say I'm rejecting you. I cross that out because it's no longer something that I'm going to consider that the proportion is actually 0.39. So what does that mean? If I reject the null hypothesis, what I'm left with is HA. I'm left with my alternative hypothesis, which is that p is less than 0.39. So the proportion of men in that age range who exercise regularly is probably now less than 0.39. I don't know what it is. I can't say how small it is. All I can say is that it is probably less than 0.39.